before spring break, or actually before the test. This is it. This is the end. Woo! So I think I did a recap of this last time, but just a reminder. So the test: circuits, series and parallel, resistors and capacitors, series and parallel resistors and capacitors, and then magnetic fields. Forces on charges, forces on moving charges, and also current. Magnetic field due to current carrying wire. And now today, finishing up, if you have a changing magnetic flux, it makes a voltage, i.e. it starts current flowing. So those are kind of the four, and a sentence for each one. That's what it boils down to. That's kind of the things you need to know. So, last class, just to recap what we did last class. Last class, we reminded ourselves of the word flux. How much field lines go through some closed loop. Literally, like, think of it like arrows, the amount of arrows that go through some closed loop. We then said if that flux is changing, it makes a voltage. I'm seeing if I can find my wire, but it's gone. That's so sad. If that flux is changing, if you get more or less field lines, so when our loop was lined up, say the field was going left to right, my arms with the wire now, you get the maximum amount, and then as that loop goes kind of flat, you get less and less and less, and that was the whole rotating it thing. So we reminded ourselves that flux was how much the field is, times the area, times cosine of the angle. There it is, it's on this thing all over the place. And the voltage generated, we just say how much does that flux change every second. And that gives us the voltage. And it was a good time. We had so much fun. It was very just a bunch of math with it. Finding the change. We changed the magnetic field. We changed the area. We changed the angle. And we did all three versions of that. And really tried to stress this is what makes this electromagnetic force, it's voltage. It makes current flow. And then we said you're going to add a bunch of loops of wire, so check an N in front of it because you want to make a large voltage. Each loop contributes. You have 10 loops. Multiply that changing flux by 10. You have 1,000 loops. It makes it 1,000 times the voltage. 10,000 loops, 10,000 times the voltage. So the reality is these things have a bunch of loops to them. Okay. Rotating loop. Woo, talked about that. Talked about a generator at the end. Very nice. Is this worth talking about? No, I don't know why I have this. This will show up on the final. I think last year I had more time, so I was like, yeah, let's check in some review questions, make certain things. This is a good question to kind of go through. I'll try to put the solution by the end of class or whatever, but we're not going to focus on that today. Today we do have stuff to get through. Okay, so last class, we calculated the voltage that is made. That was the whole thing. We did math. A lot of today is finding the direction that current will flow. All our classes kind of boil down to this. You get a value, you do the math, but you also need to figure out the direction. That's been the narrative with magnetic fields. We did math to find the force. We had to use the right-hand rule to find the direction. We did math to find the magnetic field. We had to use right-hand rule to find the direction. We did math to find the voltage. We're going to use right-hand rule to find the direction that current's made. All right, but this is what we're going to be spending most of today on, is this idea. It's called Lenz's law. It says the direction of the induced EMF drives current around a wire loop to always oppose the change in magnetic flux that caused the EMF. And that's a lot of jargon. And I'm going to summarize it in a much easier way. Current is generated. Wires don't like change. They don't want things to change. That's going to be the mantra for this whole thing. These loops of wires do not want the flux to change. They do not want the flux to change. So that's going to basically be how we're going to solve every single problem. We're going to say, how is it changing? How can I make a current to oppose that change? I don't want the change. These loops do not want the stuff to change. So we're going to go into some problems and we'll kind of unpack that. It wants the magnetic flux to be constant. It wants to keep the same amount of field lines that it started with. Okay? So we're going to look at some examples, and these examples are going to help us unpack that logic. It's a really simple statement. We're going to have to do some application of it, though, to understand what it looks like in practice. Lenz's law says we don't want things to change. So we're going to make a current to prevent that from changing. Okay. I'm going to come back to this, and I'm going to go ahead and jump right into examples to unpack this specific situation. So I got a bunch here, but I'm actually going to just focus on one. I'm going to crop this picture and just focus on one example, and I'm going to kind of talk through the logic, and then I'll put the logic in writing after that. But if I put the logic first, it's going to probably be too much information and be a little bit overwhelming. So let's just look at one example here. We're just going to look at this example and kind of talk through what's going on here. So this picture may be a little unclear what's going on, so let me explain that. I have a loop. So this is my loop. And we're going to specifically look at this scenario. This specific scenario is going to be one we're also going to visit mathematically. But for now, I've got a loop of wire. And this rod on the right side is sliding to the left. This rod here is sliding to the left. So it starts where I drew it. It starts here. And at some later point, my loop is now, and I'll do it in a different color. So my beginning is in the red color. My end is going to be, let's just do green. This is my new loop at the end. The rod is moved. Okay, so I have my beginning situation. And in fact, here, through the magic of copying and pasting it, this is my later situation. The rod has moved a bit to the left. Okay, so it started, a big loop, and it went down. So let's kind of talk about what's happening here. Everything's in terms of flux. Everything's in terms of the number of field lines. So I have this big old area to begin with. I want you all, so which way is the magnetic field pointing? You can just holler it out. Out of the page, so these dots, is that out of the page, into the page, up, down, left, right? Out of the page. Awesome. So I have a bunch of field lines pointed out of the page. Now, when this thing shrunk, did I get more of them or less of them? Less of them. In my new position, I have less field lines going through it. My flux has gone kind of down. I have less field lines pointed out of it. Remember the mantra. We don't like change. We don't want that change. This wire doesn't want, this again, I'm personifying this, whether a wire has wants and desires, but that's the way to think about this. It doesn't want less. So the question is, what do I do? If I don't want less, what do? I make more of them. So I used to, let's just kind of, again, me shrinking the picture kind of didn't do this justice, so let's go ahead and take this and make it big like this one. There's no easy way to do this. My rod is now here. Let's color this in. Let's just kind of count the dots. This is kind of a helpful way. This one up here had six things going out of it. This bottom one had 4 things going out of it. I lost 2. We don't like change. So what do? I make 2 more going out of the page. How? How do we make more magnetic fields? Current. We make a current. So, to oppose that change, I went from 6 to 4. I lost 2 of them. What do? All right, let me make 2 of them. How do I make 2 of them? I make a current. And my question to you all, which way will that current be? To make a magnetic field pointed out of the board, will my current go clockwise? Well, that's not clockwise. Clockwise or counterclockwise? I'll give you all, this is where right-hand rule 2.5 is really handy. If I want to make a magnetic field, if I want to make a magnetic field out of the page for a current carrying loop, do I make my current go clockwise or do I make it go counterclockwise? Which way should I go? Which way should current flow? This way or that way? Give you all a few moments, see if you can figure it out. If I want to make a magnetic field out of the page, which way does current need to flow? And this is what we're going to spend most of class today practicing. Just doing this. So this is where right-hand rule 2.5 is really useful. Remember, right-hand rule 2.5 said if you have a loop of wire, you can just curl your fingers in the direction of current and your thumb points in the direction of the field. So if we look at our picture here, if I want to make a field out of it, my thumb's out of it, so which way is current? Counterclockwise. To make a field going out of the page, I will make a current going counterclockwise. So for those online, if I want to make more going out of it, counterclockwise, thumb points out of the page. Okay. So this has a few steps. You ask yourself, am I getting more field lines or less field lines? How do I counteract that? How do I make a current to make that happen? That is what we're going to be practicing. And that's what's written right here. So you draw a picture. If a picture is not given, classic, draw a picture. Determine, am I getting more field lines or less field lines? I'm going to make a magnetic field to oppose that change. If I'm getting less, I want to make more. If I'm getting more, I'm going to make it the other direction to cancel it out. If the magnetic flux, and I don't like I'm using the word, let's see. Determine whether, let's just put this in layman's terms. This is more official jargony words, but let's go ahead and change this to what is magnetic flux. Determine whether you are gaining or losing magnetic field lines. That's all flux is. Am I gaining or losing magnetic field lines? The induced magnetic field opposes that change. If gaining field lines, induced field will be in opposite direction. So if I'm gaining field lines into the page, how do I cancel that? I make magnetic field lines the other way. If I'm losing field lines, magnetic field lines, induced field will oppose that. So I will, if losing magnetic field lines, make more field lines in original direction. So if gaining field lines, make field lines in opposite direction. Remember the mantra, everything in this boils down to oppose the change. Oppose the change. Oppose the change. We make a current to make a magnetic field to oppose the change. And now we're just going to do a bunch of examples of this. Finally, I can explain to you. So remember I told you all, I kept saying this, that the flux is negative. The change, the voltage is the negative change. The negative sign. Oppose the change. This negative sign, this is why it exists. The voltage will oppose the change. That's the mantra. That's the thing. Oppose the change. Avoid it. Or not avoid it. Try to cancel it out. So again, now we're just going to do a bunch of examples. We're going to find out, are we gaining field lines or losing field lines? We will then make field lines to oppose the change, and then we'll make a current that makes that happen. 3 steps. Okay? This has the most steps in it, but once you, again, like all the right-hand rules, once you do it enough, you'll be good to go. These just take practice, but it's very recipe-based. Yeah?
With the direction of the velocity have anything to do with it?
Yeah, so that's whether or not you're gaining field lines or losing them. So like in that last problem, if the thing was moving the other way, we'd be gaining them, so we'd actually do the opposite.
Okay.
Yeah, that's a great question. And let's see, do I have one just like that? Yep. Part D, number D is the exact, yeah. So, let's go ahead and look at B. Again, we're just going to be doing each of these in pieces. So, B. Let me make this even bigger to make it easier to understand or easier to see. I have a loop. I have a loop that originally is in a field, and it's leaving the field. It's going from a place where there's field to a place where there's no field. So first question, am I gaining field lines or am I losing field lines? Think about that for a second. If I go from here to there, if I go from a place of field lines to a place of no field lines, am I gaining them or losing them? I'm losing them. Oppose the change. If I'm losing them, I don't want to lose them. So what do? I make more of them. I lost them. I don't want to lose them. So let me make more of them in the direction that they originally were. They're originally out of the page, so I'm going to make some out of the page. And then the last step. What's the direction of current? Point your thumb in the direction of that. Bam, counterclockwise. To make magnetic field lines pointed out of the page, you just point your thumb out of the page and your hand goes counterclockwise. So to make that happen, we make a current counterclockwise. And every single problem is going to be the same recipe. Am I gaining or losing? How do I oppose that? Make a current that makes that happen. Okay. Try C on your own. Try it out. Go through the process. Am I gaining or losing? If I'm gaining, make them in the opposite direction. If I'm losing, make them in the same direction. Then make a current that does that. So C, I'm starting out of the field, and at some point later, I'm completely in the field. It starts up here, and it ends, in the field. So kind of breaking this into the 3 steps. First step, I'm gaining B out. As it goes down, I'm getting more of them out of it. Oppose the change. Step 2, how do I oppose gaining B out? Make magnetic fields that are in. How do you cancel them out? You make them the opposite direction. So now that it's down here, oh no! I hate that I have more of them. Let me make some the opposite direction to cancel them out. Oppose the change. So I'm gaining magnetic fields out. So to oppose that, I make B in. How do I make that happen? Thumb goes into the page. And that is clockwise. Right hand rule 2.5, current clockwise. To make that happen, I make a current this way. This is the main goal. What's the point of these problems? It's to find the direction current will flow. That's the whole point. Every step 1, step 2 are just things to get us to step 3. That's the question I'll ask you on a test. Hey, here's a picture. Which way will current flow? Basically take any one of these and they're good test questions. And the punchline will always be, which way will current flow? Clockwise, counterclockwise, no current. All right, try the next one, y'all. Step 1, step 2, step 3. Am I gaining field lines or losing them? If I'm gaining them, which way am I gaining them? 2, how do you counteract that? 3, use right-hand rule 2.5 to find the direction of current. Very recipe based, very recipe based. So once you can do 1 or 2 of these on your own, you can do every single one. So this is the exact opposite of A. So my rod at some later time is now over here. So I've gained magnetic field lines that are out of it. My loop has more of them. When it moved to the right, I have more of them. How do I counteract gaining them? I make the opposite. So I make some B that are in. So I make some magnetic fields to cancel those out. And then the punchline is the exact same. If you have that, then the I is going to be clockwise. Right-hand rule 2.5. Clockwise. To counteract that change. It's all about how do I oppose the change? Which way do I make current to oppose the change? Okay. Try the other ones. I was like, it's just practice, practice, practice. Nothing more to be said. Just like all the right-hand rule stuff, you just have to try them. And I'm going to give you all some time, but I'm going to give you the answers, just so in case. I will go through the steps, but I'm actually going to go ahead and just put the answers real quick so you can see whether or not you're doing it right. All right, so I'll give you all a moment to kind of, there's the answers, see if you can get there. For E, it is clockwise. For F, it's counterclockwise. All right, so in the first case, if B is increasing, I am gaining B that's out. So same thing as before, I'm going to make a B that's in. Right-hand rule 2.5. If I want to, same as the last ones, to counteract that change, thumb goes in, clockwise, woohoo. For the last one, I am losing B out. I'm losing magnetic field lines that are pointed out of it. How do I counteract losing them? I'm going to make magnetic field lines that are out to counteract that change. How do I make that happen? Current that's going counterclockwise. So this is the direction that current will flow. Which is meaningful. It's important to know which way the direction matters. Direction matters. Which way current flows matters for all sorts of devices on a functional level. And this is why on the motor, at some points it's gaining field lines, so it makes current one way. At some point it's losing field lines, so it makes current the other way. And so that makes a current that goes counterclockwise, clockwise, counterclockwise, clockwise, counterclockwise, clockwise. That's called AC current. That's what comes out of your wall. Out of your wall is not a current that's constant. In fact, if you want to charge anything, you all have these blocks that get plugged into the wall. Those things convert that flip-flopping current to current that goes one direction. So that's the application here. That's why that's like one use of this, why it's meaningful. Yeah, it's just practicing it. Nothing exciting, nothing really. This is just a practice. Okay. So now we're going to look at a couple, actually let me make a problem that's a bit more aligned with kind of the way I've been showing it, and then I'm about to show you one that's going to look different, and we're going to try that one out. So a loop of wire starts in a place of no magnetic field. It then enters a field pointed into the page. Which way will current flow? Will it be clockwise, counterclockwise, or no current? This is one where you're going to draw a picture. Make you all draw the picture. I'll draw it halfway while this question's open, but to give you all kind of a checkpoint to work off of. So a loop of wire starts where there's no magnetic field, it then enters a field pointed into the page. Which way will current flow in that loop? Oh, another application of this is how wireless charging works. So your phones, when you put them on that pad and they charge up and nothing's plugged in, you have a loop of wire in your phone. The thing below it's got a loop of wire. It makes a changing magnetic field that induces current in the loop of wire inside your phone, and that current is how it charges it. It's called inductive charging. This is how it works. Make a changing magnetic field, have a loop of wire in your phone, ta-da, you made current in your phone. That current can be used to charge the battery. You made a voltage in it, which then can charge it up. So this is why not all phones work with inductive chargers. Your phone has to have the loop of wire in it to actually pick up the changing magnetic field. If it doesn't, it's not going to do anything. All right, so I'm going to draw the picture. So I have my loop originally here, and it's going to enter this, a magnetic field pointed into the page. So it starts over there to the right, and at some later time, it's going to be inside there. So that's the picture. Which way will current flow to oppose that? And this is also going to give me a sense, oh, the clicker base wasn't working. It's so sad. Oh, well. I want to see the responses, but everyone's going to see the responses. Sure, let's see the responses. There you go. I mean, that's going to bias some people to B. I have no idea if B is right. I haven't done it myself yet. I haven't spent the 10 seconds. So who knows? Maybe A's right. Maybe don't follow the horde. Unless you have absolutely no idea. Anyway, all right, let's talk through this one. I'll leave it open. I did kind of show the answers so that, well, I showed the responses. Okay, so I'm getting extra field lines pointed into the page. I don't want extra field lines pointed into the page. How do I oppose that? When my loop is now over here, I say, no way, Jose. Get out of here. I'm going to make some magnetic field lines pointed out of the page because I don't want it. How do you make that happen? Right hand rule 2.5, thumb pointed out, curl your fingers, woohoo. Counterclockwise. Oppose the change. I'll close it out in 5, 4, 3, 2, 1. So it turns out the horde was right. There you go. Look at that. Mob mentality. It works. All right. How do I... So there you go, y'all. That's the idea. This is kind of the simplest case I can give you. Yeah.
So if there's like base like that, would there be like a rule that it would be clockwise or counterclockwise if they're like out? If the current is pointed out in that one, is there a reason that it's counterclockwise always if it's always increasing? Like, you know what I mean?
it's really hard to make a bunch of like set rules for it because there's so many different situations. I could be entering a field that's pointed into the page. I could be entering a field that's going out of the page. I could be exiting a field going into the page. I could be exiting a field going out of the page. I could be decreasing the area of the loop. I could be increasing the area of the loop in a field that's either into the page or... So it's really hard to make just like a if this, then this. You kind of have to go through the logic because the number, all the different permutations are too many to make a big list of. I mean, you could try to make a big list of it. I could have this loop rotating, in which case I get less field lines going into it. I could have the field increasing, I could have the field decreasing. Yeah, so I don't know if that answers. Yeah, unfortunately you can't, you can try to make a big list, but you'd have to consider, so you'd have magnetic field lines going in, magnetic field lines going out, and then you'd have to do every single possible. It's a lot of permutations. So unfortunately, the easiest way to do these is just to kind of know the rules. Yeah, if it was just a short list of if this, then this, I'd just give that to you all, because that would be easier, and if it works, it works. But in this case, the rules is the easiest way that I know of. Yeah, that's a good question. All right. Here's another one. And this one, so I told you all that permanent magnets, I'll read the problem, and then I'll tell you all the thing you need to remember for this. And the north pole of a magnet is moving towards a loop, as shown below. If you were looking at the loop from above, which is kind of like we're looking at it, would you say that the induced current is clockwise, counterclockwise, or zero? And to clarify clockwise and counterclockwise, I'll draw it on the picture. So clockwise would be this way, counterclockwise would be the other way. So those are the two, or zero. Before I even open this question, when we talked about permanent magnets, I told you there was only two things you need to know. One of them, every magnet has a north and south pole. You cannot find a magnet with just a north pole. You cannot find a magnet with just a south pole, as far as we currently understand how the universe works. If you discover a north pole, a unipole magnet, you win the Nobel Prize. That's how big the deal is. Okay, that was one thing, north and south pole. The second thing was which way do magnetic field lines point on a permanent magnet? So I'm going to give you all a few moments to think about that before I even open this question. Which way, so on the north end of a magnet, do the magnetic field lines point away from it or towards it? This is the thing that's really important to remember. Do the magnetic field lines point away from the north end or towards the north end? And I'll tell you the answer in a second. They point away from it. The magnetic field lines point away from the north end of a magnet. The magnetic field lines point away from the north end of a magnet. So, as this thing gets closer, do I get more of those field lines that point away or less of the field lines? Go with your gut there, and then go through the steps. So am I gaining, as this thing moves downwards, this magnet's going downwards, do you think you get more of the field lines pointed down or less of them as that magnet gets closer? And then counteract that change, right angle 2.5 to make it happen. I'm going to restart this problem. The physical clicker base, I guess I didn't have it plugged in all the way. I don't know. So I'm going to restart this problem and just delete that last one. In case anyone in class is a physical clicker, but also for my benefit. This lets me see how people are responding. And it's totally not, oh, yeah, great, it's working. Okay, cool. Alright, so I'll delete, make sure you respond to this one again. The last one I'm just going to delete that. So which way would that current go? Clockwise, counterclockwise? And I drew the counterclockwise and clockwise on there just so you had a frame of reference of what I'm talking about. Alright, we'll go to 50 seconds and call it good. In 5, 4, 3, 2, 1. Okay, so again, it's that same logic that we've been using. Am I gaining field lines or losing them? So, as this magnet gets closer, rely on your experience with fridge magnets. The closer a magnet gets to something, the stronger that magnet seems to be. So the closer this gets, I get more field lines. The stronger the field, the more field lines I have. The more field lines there are, the stronger the field. The less field lines there are, the weaker the field. So as this magnet gets closer and closer, I'm getting more and more field lines pointed down. As this magnet approaches this thing, so at some point later, I have way more of these things going through it. I've increased it. So what do I do? Well, remember, we don't like change. We're going to make a magnetic field line to oppose that increase. It's increase there. So then we put our thumb up, we curl our fingers around, and the answer is counterclockwise. How we do? Oh, pretty good. Great. Doing this is probably one of the trickiest kind of things because it's a lot of spatial reasoning kind of going on here. So if you all are doing great, it looks like you're doing pretty good, and that's awesome because this stuff takes a little bit of takes a good amount of processing to kind of go through it. Okay. Let me read this problem before I open it, just to clarify what's going on here. The north pole of a magnet is at a set distance from a copper loop, which is rotating as shown below. To clarify, this loop is rotating like a hoop, like this. It's rotating like this. It's not spinning like a coin spins on a table. It's just rotating in place, like this. The loop is just spinning. Take a loop, like a steering wheel. The loop is spinning like a steering wheel. There we go. This loop is spinning like a steering wheel. The magnet is stationary. Which way will current be induced? Will it be clockwise, counterclockwise, or will there be no current induced? So, go through the steps. Am I gaining magnetic field lines, losing magnetic field lines, or not changing magnetic field lines? If there is a change, counteract it, make a current that makes that happen. So again, this loop is spinning like a steering wheel. So at some time, let's just pick like a dot on it. At some point, this dot's here. And then this dot kind of rotates to this spot. And then at some point, the dot rotates to this spot, like a steering wheel. All right, we'll go to 1:10 on this one. All right, we'll close this out in 5, 4, 3, 2, 1. I'm pretty pleased actually with the responses here. You're going to see and be like, why is he pleased with this? They're all over the place. But I'm really pleased at how many people got the right answer. As weird as it sounds, it's not that many. But this is I don't want to call it a trick question, but I haven't given you one like this. So, what's going on here? The magnetic field due to the north end of this magnet is pointed into the loop. If the loop rotates like a steering wheel, I don't get any more lines, I don't get any less lines. The number of field lines is the same. So who cares? Turning that loop in place like a steering wheel, I don't get more arrows, I don't get less arrows. The loop just, again, you can imagine if I had a loop like a hula hoop and I'm in the wind and I just spin it in place, I don't get more wind through that loop. It doesn't change anything. If I do not get any more field lines, if my flux doesn't change, there's no current. You have to have a changing flux. You have to have a changing number of field lines. So, orientation matter, that kind of thing. If this spun like a top, like it spun like a coin on a table, then we would get a current, and it would depend which way it's spinning, and that'd be really hard to word, so I wouldn't try to do that because it'd be confusing. All right. So there you go. This is kind of all, I've given you kind of all the different scenarios. This set, if you want to make certain you got this, just like before, this is literally from the problem set, all these 6 examples. Practice through these. Now we're going to get into a couple specific examples, and that's going to kind of be it. It's actually going to be something we've already seen before. This thing. It's the moving rod. It's a kind of a specific case of these. It's a nice kind of problem to give. So, this question, again, I'll read through it and clarify what's going on before I send it to you to start thinking about. What is the flux through the current loop shown below? What am I referring to here? So what I have here is I have a rod, and we've kind of already seen this, and I have a wire. And this rod can slide on the wire to make the loop bigger or smaller. All I am asking you for right now is what is the flux through this loop? This is my loop at this time. This is a closed loop right here. What is the flux through that? It says X is 3 meters, L is 2 meters, and the magnetic field is 3 times 10 to the minus 6. What is my flux through this loop? So again, just remembering what is the equation for flux, calculating it. This is a very specific case for flux. It's just kind of a classic type of problem and test you understand what's going on with flux. That's it. Real world application wise, there isn't one. So this is just kind of a, do you understand what's going on? Can you do flux? And we're going to spend a few slides on this specific type of problem. And notice that the units on these are all different. Only one of the units up there is right. Whichever one has the right units is the right answer. So you can do the math and you can look at the units. That was purposeful. All right, we'll go to 1:30, so 15 more seconds. And we'll close this out in 5, 4, 3, 2, 1. All right, so really straightforward. Magnetic flux equals B times A times cosine theta. The angle here is that area vector. The angle between the area vector and the magnetic field, they're the same direction. So this just equals theta equals 0. So that goes away. So it ends up just being 3 e to the minus 6 times 3 times 2 to get the area. And that comes out to 1.8 e to the minus 5. The units come from the math. The unit for magnetic field, T. The unit for area, meters squared. Boom. And did pretty good at this. Great job, great job. Okay. So again, this problem's a classic. It's easy to kind of give you a picture for this. And we've already talked about this as well. So let's see. Get rid of this. This is the clicker question one. If this rod moved to the right, which way will current flow? So my rod is originally where it's shown on the picture. If that's the rod's moving to the right, so at some later point, now it's over here. The magnetic field is pointed into the page. Which way will current go to oppose that change? Yeah.
The question says left. Do you want us to do it right?
Yeah, that's a great point. Which way would current... I don't know what I was doing there. There you go. Thank you. Which way would current flow if the silver rod moved to the left? Thank you. That's going to confuse so many people now. Left. There it is. That's the right picture. Move to the left. Magnetic field still into the page. Yeah, the last slide said to the right, and I just assumed this was the same. So which way would current flow if the silver rod moved to the left? Go through the steps. Did I gain magnetic field? Did I lose magnetic field? Whatever happened, oppose the change. Make a magnetic field that does that. Make a current that does that. Nice. Answers are 50-50 between two. Now, how much of that is the delay in the stream and people seeing if it's to the right? We'll see. I'll leave this open a little bit longer. So we'll go to 140 just to give time for my thing. Nah, there's still 50-50. All right. Again, we'll go 10 more seconds. And we'll close it out in 5, 4, 3, 2, 1. All right, y'all. So let's go through our, again, 3-step process. Am I gaining or losing? I am losing magnetic field that is in. It used to be on the right side. I used to have a bunch of X's. I've got less X's now. I'm lost them. So what do? I counteract that change. I'm going to make B that are going in. I lost them. I don't want to lose them. So I'm going to make some magnetic field that are going in. There we go. There they are. How do I make that happen? Thumb goes into the page. Current's going to go clockwise to make that happen. Current clockwise. Current clockwise. All right. Now, just to make me feel a little vindicated. Ooh. Which way would current flow if the silver rod moved to the right? And I will do the magic of just deleting all the ink on here. Boom! So now it is the thing I originally said. Which way would current flow if the rod instead was over here? It moved to the right. Did I gain field? Did I lose field? Counteract the change. Sound like a broken record. The great news is if you hear me saying this broken record stuff and you're like, I get it, like, why do you keep repeating it? That's awesome, because this is traditionally quite tricky for a lot of people. This whole idea, this 3-step process, figuring out which way current flows, is traditionally one of the trickier things to kind of understand. So that's why I'm spending so much time on it. That's why I'm repeating. Because it's funky, this whole opposing the change, this 3-step process thing. So, all right, we'll go to 1:15, so 20 more seconds. We'll close out in 5, 4, 3, 2, 1. All right. So, moves to the right. I get more. So, gaining B that's in. So, I'm going to make B that's out to oppose that. However much it may be. And the current's going to go counterclockwise to make that happen. I counterclockwise. Bam. And, I mean, it makes sense. It's the exact opposite of the last problem. So the answer is going to be the exact opposite. All right. Don't worry about this one. Good question to kind of think through. I'm just going to put the answer. You can come back if we have time. We'll maybe come back and look at it. Otherwise, feel free to look at this later. But I'll just put the answer so you have that. Okay. So we did all the conceptual. Which way is the current going to flow? Here's the math. The voltage that is generated in this specific scenario, which is just kind of a good one, is just BLV. So it comes from the equation of, so let's just kind of write this out in non-calculus version. Change in flux with respect to time. So then we say the change in B A cosine theta with respect to time. The magnetic field is a constant. The angle, it's 90 degrees, so it goes away like the other cases. So I have my change in area over change in time. What's my area? Let's just go ahead and unpack that one more step. My area, so change in length times width. We're going to call this thing the length. We're going to call this thing the width. My length isn't changing. My silver rod isn't getting any bigger. It's not getting any smaller. So I get BL, change in width, change in time. And if you all remember from your physics 1, and actually, you know what? Let's just use the variable that's on this picture. The width is x here. That's how far. Change in x over change in time. That's just velocity. You don't need to know this derivation. You do need to know that, let's just put it over here. Epsilon equals BLV. Let's just make it more clear, not have a bunch of things in between it. If I give you this specific problem and I say find the voltage, this is on your formula sheet. This is one of the equations on there. It's a very specific case of this. It's just a classic problem. Has very little to no real world application that I can think of. But there's a chance, this problem is such a classic that I just kind of got to go over it in case it shows up in the MCAT or something, and to be consistent. It honestly doesn't benefit you all. I mean, the concept of which way current flows, that's useful. This math, but it's just such a classic that we got to kind of mention it. Now, we're going to get to an interesting real-world application of this, and it's absolutely ridiculous, and it's not actually... Maybe one day they'll use it. We'll see. But for now, I'm just kind of hyping up that there's kind of a... We're going to build on this case, and there's just this crazy situation use for it that they tried and kind of worked too well. So now I'm just kind of... Something to look forward to. It's really interesting, but we'll get there. It's kind of the last thing we're going to do today. All right, so, let's just do a problem with this. Really simple, very straightforward, but just to make certain we're kind of cool with it. Anytime I give you all a new equation, I kind of like to do that. So the rod shown below moves to the right on essentially zero resistance rails at a speed of V equals 3 meters per second. If B equals 0.75 Tesla everywhere in the region, what is the current through the 5 ohm resistor? Does the current circulate clockwise or counterclockwise? Something that is kind of cool with this. So back in the day, there used to be physics labs. I guess there still is, but they were different. One of the labs they did was you built something like this. So you had a magnetic field, and you literally had these rails, and you had like a rod that rolled on it. Well, what you would do is you would actually do the opposite. You would pump current through this thing, but then it didn't like it because it changed the flux, and it would actually shoot your rod would actually experience a force and get pushed off to the side, and it kind of shoot off like a little gun kind of thing, which is cool because it doesn't like change. So it actually makes itself roll to counteract that change. It was a nifty kind of lab, but I just have memories of doing that one. Anywho, let's write down our givens. We have velocity. The good news is with this problem, if you see this picture, you immediately know what equation to use. Like these problems, if you see this picture, we're gonna use that the voltage equals BLV. If you see this picture, you're gonna use it. So it's really straightforward at least. V equals 3 meters per second. B equals 0.75 Tesla. And we have a resistance. That's weird. Why is that there? We'll find out. What is the current? That is what it's asking for. Okay, so I told you all if you see this picture, you're going to use EMF, i.e. voltage. Remember, EMF is voltage. That's a really important thing to have somewhere in your head. EMF equals BLV. Nowhere in that equation does it have current. So I want you all to spend a few seconds, few moments. How am I going to actually find current here? That equation doesn't have it. What am I going to do? Think about it for a bit. See if you can think what the next... We're going to use that equation. But then what? So remember, EMF is voltage. I give you resistance. If you have voltage and you have resistance, V equals IR. EMF is voltage, effectively. So, hey, we find the voltage, plug it into V equals IR, solve for I. Easy peasy. I had to give you the resistance for you to actually solve this problem. A wire has to have resistance for you to calculate the current. This is the only way to calculate current in a wire is V equals IR. Well, when it comes to at least electricity. I suppose if you measure the magnetic field and blah, blah, blah. All right, so cool. Let's find the voltage. So EMF equals 0.75. This is a huge magnetic field. Anything near 1 Tesla is huge. Oh, it wasn't written in the problem. You're like, what's L? It's in the picture. So this is again one of those, if sometimes you're like, I didn't write down all the givens, you can always go back. This is L. It's in the picture. It wasn't actually worded in the problem. And it's gone. That's L. That 4 centimeters, the length of the distance there. You need to be very careful with these problems. I will give you in a problem L, and I may also give you this. Now, if I give you that 3 meters, guess what? It's absolutely useless. You need to know what L actually is. It's the length of the rod. Subtle, but it's one of those things you just got to know. What does L correspond to? What does the variable actually correspond to? It's the 0.04, the 4 centimeters, 0.04 meters. One of the skills from a physics class is being able to look at variables and know what they mean. Oh no, ghosts! All right, go ahead, y'all. Try to continue solving it while I spook away the ghosts. It did the thing. So yeah, go ahead, see if you can figure out the answer, and then I'll kind of zoom through it. So solve for the voltage, B times L times B. L is 0.04. V is whatever it said in the problem, 3 or something. Find that, plug that into V equals IR. You know R, you know V. Solve. And I would tell you what the answer is, but I don't have any of the numbers memorized. That's why I write them down. Okay, the ghost is gone. All is well in the world. L equals 4 centimeters equals 0.04 meters. So the EMF equals 0.75 times 0.04 times 3 equals a number. Remember, y'all, it's hard to make a strong voltage. Even if you have a strong field, if you want to make a strong voltage, you need lots of loops. And then we're going to use the second equation, 0.09 equals I times 5. So I equals that divided by 5. 0.018 amps. And the last question, which way will current flow? The math doesn't tell you. You have to do, am I gaining fields? Am I losing fields? Go ahead and think about it. The current is going to go clockwise. My rod at some later point is over here. I've gained field lines. Gained. B out. Make. B in. That's going to result in a current that is clockwise. All right. So much fun. Again, there was a bunch more dots. Get rid of the extra dots by putting some magnetic field in the other direction. And there you go. Look at that, I need more space. Okay, so this is where we're getting to the really interesting, kind of crazy case we did. What would happen if I just had a conducting rod moving to the right through a magnetic field pointed into the board? What's really cool about there's no loop here. There is no loop in this picture, but something's going to happen. And why is something going to happen? Remember, y'all, inside this rod are a bunch of electrons. And if the rod is moving, the electrons are moving. If I have moving charges in a magnetic field, I want you all to go and figure out which way. You know what? Let's make this a clicker question. So, let's take this picture. Oh, it's so many pictures. This is the dedication I had when I made this. I made all these X's and dots and hand-drawn. Well, not really hand-drawn. All right. Electrons are moving to the right in a magnetic field pointed into the page. What direction will the negative charge? What direction will the negative charges go? Let's just put it that way. Which way will they experience a force? Will it be up, down, left, or right? Throwback, y'all. Right-hand rule. I have negative charges moving in a magnetic field. Which way will they move? Sporadically throughout spring break, definitely just do random right-hand rule problems because these ones are so easy to make a mistake on. Just like every now and then, pick one to do. Make sure you don't mix up right-hand rule 1, right-hand rule 2, right-hand rule 2.5. Wow, we're evenly split between 3 answers. Not what I expected. But again, it means it's a good problem. Whenever I get a bunch of different answers, it's a great problem that I asked. In the sense of, it's important that we kind of look over this again. Alright, y'all. So, the trick to whenever it comes to what direction will they move, i.e. which way the force. Remember, y'all, your thumb is the strongest finger on your hand. Your thumb points in the direction of force, and then that can kind of help you remember the rest of it. Your fingers go in the direction the charge moves. Your palm goes in the direction of B. The thumb will be in the direction positive charges move. Your thumb will be in the direction positive charges move. All right, we'll go to 150. We'll close this out in 5, 4, 3, 2, 1. All right, so my charges are moving to the right, fingers to the right. My magnetic field is into the page. Thumb points up. If they were positive charges, awesome, but they're not. They're negative charges, so they're going to go down. So fingers in the direction of the charge, direction of motion, magnetic field into the page, thumb points up, but right hand rules for positive charges. So these are going to go down. So why is this interesting? Why does that matter? So that means, in this case, all these negative charges are going to build up on the bottom. And if I lost, where do these negative charges come from? The rod. That means I'm going to get a buildup of positive up here. If I have a buildup of positives and a buildup of negatives, I have a positive voltage up here. I have a negative voltage up here. You've made a potential difference. And also the fact that charges move, that's current. So what's really wild is if you just move a straight piece of wire, it doesn't have to be connected to anything. If you move it fast enough through a magnetic field, you generate a voltage, which generates a current. You'd be like, what? How is that going to be useful? I already told y'all it's really hard to make a strong voltage. So then the question is, what's the point of this? Well, fun fact, the equation for this is the exact same equation as the thing we did before. If you want to calculate this voltage, it's BLV. It's the exact same one for the closed loop. Turns out the loop doesn't matter. The moving rod is all that mattered. So that's kind of cool. And then now we get to the fun thing that's really interesting. If only we had a magnetic field all around us. We do. What if we made this wire really, really long and moved it really, really fast? Where would we do that? Well, it's really hard to move things fast on Earth because of air resistance. So this is legitimately something that happened. On the space station, they released just something, and it had a wire, and they made this wire super long. I forget exactly how long. Really, really long. Actually, is the last one with the math? Yeah. Do the math. They had a 20-kilometer long wire. Wild. Super. It's space. You got as much room as you want. What are you going to run into? Super long wire. They're in space, so they can move super quick, 10 kilometers per second. I mean, when you're going around the Earth, you can go super fast. Nothing's stopping you. The only reason it's hard to go fast on Earth is air resistance slows you down. But Newton's first law, an object in motion remains in motion. So it's really easy to go fast in space. So they had a super long wire in the Earth's magnetic field, which is very weak, but going super fast. Calculate the voltage that it makes. Just V equals BLV. Epsilon equals BLV. Just really straightforward. You just multiply. Now you have to convert. Don't forget to convert your units. You got to convert the kilometer long wire. Convert that to meters. You need to convert kilometers per second to meters per second. Just like converting kilometers to meters. Oh gosh, there's answers all over the place. All right, I'm just gonna keep work through this one. So this is my length. So this is my B is already labeled. So that's my velocity. So we have a magnetic field of 5 e to the minus 5. That's really small, but the other numbers are all really big. We have a 20 to the third meters, and we have a 10 to the third kilometers per second You plug all that in. And you get 10,000 volts. $10,000 Wild. I mean, that's a crazy long wire. Like that's the challenge here. And they legitimately did this, tested, because it's like free electricity. Literally just send it like, you don't have to do anything to keep this wire going. They will experience somewhat of a force. There will be somewhat of a force kind of acting on it too. Yeah, it's wild. I'll go for like 10 more seconds just to make sure everyone sees the answer. Let's see. How we doing? Oh, look at that. Everyone got the right answer. Well, most people. All right. 3, 2, 1. Awesome. Whoa, good job, everyone. So good. But yeah, there's a video of this. Feel free to kind of watch on your own time. They did this. They tested it out. It made 3.5 kilovolts. Could have made more, but so one of the challenges here is so the wire was insulated. I don't know exactly why it needed to be insulated and why there was like air inside, but some of that air escaped. This is such a high voltage. So fun fact, like the lights in here, if you make a really high voltage, gas turns to plasma. That's how halogen light bulbs work. That's how neon signs work. Plasma's really hot. Plasma got hot, burned the wire, it broke. But it's just kind of a crazy idea. Let's just take a wire that's kilometers long, drag it through the Earth's magnetic field and make a voltage, and it works. It's just kind of cool. So yeah, there you go. Application, I suppose. Completely ridiculous one. It's unfeasible for a few reasons. Again, one, it's kind of hard to keep that wire integrity there. But who knows? Maybe one day. Maybe one day the solar panels, I guess, work well enough that they don't worry about it. And that's it. That's it, everyone. Again, pretty much all we did today was, can you find the direction current went? And then this specific case. Takes a lot of time because it's a complicated thing. But there you go, y'all. Nice little summary of everything you need to kind of, what I've been saying. Make sure you are cool with series and parallel circuits. Can you condense them down to one resistor and work your way back? Same thing with capacitors. Can you combine them? Write in rule number 1, force on a moving charge, force of the current carrying wire, find the magnetic field due to straight wire, loop of wire, solenoid, find the direction of it, and what we just did today. And I'll post this. This is already in there, so all this stuff will get posted. Finishing a few minutes early. If you got questions, come on down. But have a great spring break, y'all. Get a break. Try to get somewhat of a break. Also, just try to do a few here and there. Don't let the stuff leave your mind completely. Even if you're like committed to not doing much work, just do a problem here or there. Just pick a random one. Keep your mind fresh on this. You don't want to have to come back from break and make certain you then relearn everything. Keep it fresh, review, all that kind of stuff. Just little bits. Yeah, if you need a note card, they're on up here. Have a great break, y'all. I know I plan on having a great break.